And now to kick off the first block, we will play a video to introduce the main topics that we'll be discussing this afternoon, providing some context into the climate crisis and the energy industry's role within it.
Global average temperatures have increased by more than 1 degree Celsius since pre-industrial times. Since the 1950s, a particularly clear upward trend can be observed, and the last 5 years have been the 5 hottest years on record. While an increase of 1.2 degrees might not sound too drastic at first, a changing climate results in extreme weather events, rising sea levels, altered crop growth, and disrupted water systems, to name just a few of the major effects. And while it's hard to estimate the exact costs, there is little debate that the annual damage is already in the billions. But the damage stretches far beyond financial losses. In a meta-study, the EU expects climate change to impact health, ecosystems, agriculture, water supply, and extreme weather events, meaning that premature mortality will increase, ecosystems will shift, yields will decline, water supply will decrease, and extreme weather events will become far more likely. But what's the underlying cause of this temperature rise? Well, human emissions of carbon dioxide, or CO2, and other greenhouse gases are the primary driver of climate change. The atmospheric concentration of CO2 has steadily risen since the Industrial Revolution. And for the first time, concentrations not only rose above 300 parts per million, but above 400. To slow down and eventually halt rising global temperatures, we need to stabilise concentrations of CO2 in the Earth's atmosphere. However, at present, global emissions continue to rise. And without drastic change, we are on track to drive up the temperature by 3 degrees Celsius. To limit the temperature increase to 1.5 degrees, we have to reach net zero emissions by 2050, and from there on in, capture more CO2 than we emit. Long story short, with around 40 gigatons of net emissions in 2020, we are far off net zero, and it will require systemic change to get there. On the plus side, leadership around the world has recognised this issue. And in 2015, 196 parties signed the Paris Agreement, a legally binding international treaty on climate change that aims to limit global warming to well below 2, preferably to 1.5 degrees Celsius, compared to pre-industrial levels. The goal is to achieve a climate-neutral world by 2050. This goal requires drastic reduction in emissions. The spotlight here is on the energy industry, which accounts for 73.2% of global greenhouse gas emissions, and thus provides the greatest opportunity for change. It is therefore imperative to phase out the use of fossil fuels. This will require government policies to subsidise and incentivise green energy, technological innovation to deal with the uncertain nature of renewable energy sources, and a shift towards a society that is ready to adopt new technologies and adapt its consumption behaviour. 2 characteristics of renewable energy will be particularly challenging. The first is intermittency, as the energy supply from renewable energy sources is not as easy to control. The second is distribution, as renewable power plants are more spread out and call for new methods to locally match electricity demand and supply. Significant progress has already been made in the switch to renewables over the last few years. The share of renewables in electricity production in Europe, for example, has almost doubled, from 19% to 37% in the last 20 years. To meet the 1.5 degree goal, however, this pace will have to increase globally. This need for change poses a range of challenges and questions. What are the necessary levers to accelerate this change? How must the industry evolve and adapt to become more efficient and sustainable? Who are the most important players in the energy transition? And who will play what role in our clean energy future?
That provides a fitting introduction to our first keynote speaker for gridXdays, who is a very esteemed researcher and science communicator, here to talk about how we can still make it and the need to take urgent and drastic action to curb climate change. Stefan Rahmstorf holds a PhD in oceanography and since 1996 has been working at the Potsdam Institute of Climate Impact Research, focusing on the interaction between oceans, global warming and natural climate change. He's been a lead author of the IPCC report and became the first non-American scientist to receive the Climate Communication Prize from the American Geophysical Union. Stefan, it is an absolute honour to have you here with us today.
My pleasure.
So without further ado, I believe you have a presentation planned. Please take it away.
Yes, excellent. Thank you very much for the invitation. This is a really exciting meeting, and I want to use half an hour to familiarize yourself with the latest in climate science. But I will have to start with some of the basics, going back a little bit, namely to Alexander von Humboldt, the famous German explorer who in the year 1843 was one of the first, if not the first, to write that humans are changing the climate, quote, by cutting down forests and by releasing large amounts of steam and gas at the centers of industry. And I think he was ahead of his time there. He probably knew about the greenhouse effect because that was first found in 1824 by Joseph Fourier, but he certainly did not have the kind of detailed understanding that we have now of the energy budget of our planet, which rules the global temperature. And so in yellow, you can see the incoming solar radiation, part of which is reflected, the rest is absorbed. And in orange, you can see the long-wave radiation emitted by the surface. And only a very small part of that makes it directly out to space because our atmosphere is full of gases that absorb this heat radiation, the infrared radiation. And so most of it is actually coming back down from the atmosphere. You see that here at the bottom, this one that says 340.3 watts per square meter. And notice that that's actually more than twice as much as the solar radiation absorbed at the Earth's surface. And so the greenhouse effect is, of course, predominantly originally a natural thing, and it is very, very important. It's not a small effect. It is what makes this planet habitable. Otherwise, the Earth would be completely frozen. And so the problem now is that we are changing the strength of this effect. And if you realize how big the effect is, then it is clear that even a small percentage change in the greenhouse effect can have a major impact on global temperature. All these numbers that you see here, they are measured. We have a global radiation measurement network at the surface, and we have satellites at the top of the atmosphere measuring the incoming and outgoing radiation. And the measurements also show the increase in back radiation from the increasing amount of greenhouse gases in the atmosphere, exactly as theory predicts. So there's no question about any of this. This is just a measured fact, and the physics are understood. The problem here is now that we are increasing the strength of that greenhouse effect by adding carbon dioxide to the atmosphere. You can see this accelerating increase in the atmosphere if you look at the numbers, the year numbers on the right there, how the increase is getting ever faster. And this increase in carbon dioxide content is 100% human caused. In fact, we are pumping more CO2 into the atmosphere than remains there. So the natural Earth system, the forest, the ocean, take part of it out of the atmosphere again. Otherwise, if everything remained there, which we emit from fossil fuels, warming would be much faster still. And this increase makes a radiative forcing. So it adds 2 watts of heat per square meter Earth surface. And that is the reason why it's getting warmer. We're simply adding heat to the system. We're trapping extra heat. And that's basic physics, that the response of that is that it's getting warmer. The fact that it's getting warmer is often now shown in this beautiful depiction with the warming stripes. Yesterday, in fact, was a warming stripes day, or the day before yesterday, I think, where the World Meteorological Organization asked everyone to post on their social media the warming stripes for their country. This is the global one. Every stripe is 1 year global temperature. The more conventional view of these data is shown in this line here. And it's clear that we have been through a warming by about 1.2 degrees centigrade since the late 19th century. This warming was predicted early on. The first official expert report to the then US President Lyndon B. Johnson came in 1965, the famous Revell report, which predicted everything what's happening now, basically global warming, ice melt, sea level rise due to fossil fuel burning. And in 1988, NASA scientist Jim Hansen famously stated in the United States Senate that global warming is here now. We can actually see it in the data, what has long been predicted. And for quite a few decades now, more than half a century, global warming is actually proceeding exactly as predicted by science. If we look at the amount of warming since then, since the mid-20th century, and how much of that is human-caused, we find that actually all of it is human-caused. Within the error bars that you see here, it is all of it. If you take the exact estimate here, seriously, the best estimate, then that is that human-caused warming is actually slightly more than we observe, because natural factors have counteracted it a little bit, especially the decline in solar activity and solar luminosity since the mid-20th century has counteracted a little bit of the warming that we have been causing. I'm actually a paleoclimatologist. I've been working on natural climate changes in Earth history, on ice age cycles, for example, since the 1990s. And of course, there's a big community of over 1,000 scientists doing that. And the fruit of decades of paleoclimate research, collecting sediment cores from the deep sea, ice cores, and other sources of data, now allows us to reconstruct the global average temperature since the height of the last ice age, which was about 20,000 years ago. And you can see the warming into the Holocene by about 4 degrees, the Holocene optimum about 5,000 before Christ, and then a very slow cooling trend. This is, of course, caused by the Earth orbital cycles, the Milankovitch cycles, the shortest of which has a period of 23,000 years. And very likely this cooling would have continued, this very slow cooling, had we not bent around this curve drastically with the beginning of industrialization. And temperatures are now most likely warmer than any time in the Holocene, and that's in the history of human civilization and the history of Homo sapiens sapiens. So also the speed at which the warming proceeds here is by a huge factor faster than anything that we have seen in natural warming in the Earth history as far as we have data available. So we are catapulting ourselves out of the Holocene, the period of stable climate in which human civilization was able to thrive. Now, what we feel first and foremost is, of course, the extremes. We don't have a sensory organ for annual mean temperature or so. These are computed quantities, of course, but the extremes is what we feel directly. And for example, heat records. The monthly heat records, like a record like the hottest August on record, have increased 8-fold compared to a stable climate, a stationary climate. So out of 8 such heat records that you find anywhere in the world nowadays, 1 would have just happened by chance, because just by natural fluctuations, you can get a new record every now and then. But 7 have come in addition because of the global warming trend. And heat extremes are by no means harmless. They are silent killers. If you analyze the mortality data, you will find that the European heat wave in 2003 caused 70,000 fatalities at the time. The city of Paris had to put up tents on the city margins for all the coffins, because there was no place in the usual places where the dead people are kept before they are buried. Now, the hottest summers in Europe since the year 1500 AD have been 2018, 2010, 2003, 2016, and 2002. And that already shows you you don't need to hire a statistician to tell you this has nothing to do with a random distribution. That is simply a consequence of that strong warming trend. Likewise, we see an increase in daily rainfall records, or extreme rains in general. This is just an example analysis here for daily rainfall records. They increase because warm air can hold more moisture. Per degree centigrade of warming, that is 7% more moisture, a consequence of a basic equation of physics, the Clausius-Clapeyron equation, which tells you how the saturation vapor pressure depends on temperature. And because that goes up, you can store more moisture when it's warmer and in a saturated air mass, and that's where typically the strong rain is coming out of. And so extreme rainfalls are on the rise as predicted by physics, by climate models, and we now also see it in the observational data. The opposite of too much water is too little water, and we see an increase in drought, which has, first of all, even if the rainfall didn't change, drought in terms of the drying out of the soil moisture would increase simply in a warmer climate because the evaporation rates increase. So you actually need more rain to compensate for that. And on global average, of course, more rain is falling because more is evaporating. But there are very strong regional differences. Some regions are drying out. Typically, the regions that were already dry, it's a kind of first order pattern in the atmosphere, is dry areas are getting drier and wet areas are getting wetter. And if you look in detail, of course, it's more complicated because there's also a strong seasonality in the drought incidence. In Europe, it's mainly the Mediterranean area that is getting drier, although even in Germany, we are suffering from increasing summer dryness. And actually, the forests have been very badly affected by the drought of the past few years. In the Mediterranean, you can see that also Syria is one of the hotspots of the drying here in these observational data. And probably quite a few people know by now that in the years before the uprising in Syria, the country went through the worst drought in its history. And according to sediment data, the worst drought in at least 900 years, which led to 1.5 interior refugees within Syria because farmers had to leave their villages because the harvests failed, etc. And there is a kind of certainly a connection there. I think nobody will claim that it's the only reason for that mass protest and civil unrest that led into the civil war in Syria. But it is one of the factors that can trigger a country in this way, which is actually one thing that when I was part of a German advisory council on global change appointed by the German government for 8 years, we wrote a report about in 2007, a report called Climate Change as a Security Risk. And that found that risk scenario is that a fragile, conflicted state will be basically turning into a failed state if triggered by a so-called natural disaster like a massive drought, harvest failure or so, that then the government is unable to respond properly to, and this leading to the kind of scenario that then some years later developed in Syria and is affecting politics around the world. A very exciting area of new science is the changes in the jet stream related to resonance phenomena in the atmosphere, so-called planetary waves. And in this diagram, you see in the bottom left globe, you see the jet stream circling the northern hemisphere. And the second globe from the left shows kind of normal situation where it has some irregular meandering, and the high pressure and low pressure systems, they are embedded into these planetary waves. And now the third globe is showing a situation where resonance conditions occur with a waveguide developing, which tracks these waves and makes them quasi-stationary. So they become very big, they resonate, and they stop in their tracks. And we actually had such resonance conditions in the last few weeks. We have a regular automatic diagnostic tool at our institute running every day. We'll look at the planetary wave analysis and whether the resonance conditions are present. And so the last few weeks, we had such resonance conditions, and we did have big stationary waves leading to hot conditions in the western United States and cold conditions in the eastern United States. And the globe on the right shows a kind of similar situation, but that was in 2018 in July, where we also had a very regular, very strong wave pattern that developed there. And we believe that these resonance conditions are made much more likely because of the disproportionate Arctic warming, and because of the stronger warming on land versus ocean. That creates more favorable conditions for these large waves to develop, which then lead to these very persistent extreme weather events. Another point on extreme weather is the increase in the strength of tropical cyclones. This is an analysis published last year by US hurricane experts showing how the percentage of major hurricane intensities, so categories 3, 4, and 5, has increased over the years since 1980, since we do have reliable satellite data about hurricane activity. And the share of these major hurricanes out of all hurricanes has gone consistently up. This is something climate scientists have predicted for a long time, because the energy of these tropical cyclones comes out of the oceans. It's the heat stored in the upper ocean that provides the energy source for these cyclones. So the potential intensity, that is the maximum they can reach if they're not disturbed by shear winds or by hitting land, increases with the sea surface temperature. And so the actual hurricane intensities are also increasing, as the data, the most recent analysis show. Another logical physical consequence of warming is sea level rise, because the oceans warm up, and if you heat water, it expands. And secondly, continental ice is melting, mountain glaciers, the big ice sheets in Greenland and Antarctica, and that adds more water to the oceans, and the sea level goes up. As a background, it's worth knowing that at the end of the last ice age, I showed you that temperature curve earlier on, sea level rose by 120 meters globally, because 2/3 of the glacial ice masses were lost due to that warming by about 4 degrees. Now, that means we have about 1/3 left, and that means we have about 65 meters worth of sea level rise still locked into ice on our continents. And that means we cannot even afford to lose a very small percentage of the continental ice sheets without causing catastrophic sea level rise that will lose us coastal cities and entire island nations. Sea level so far, luckily it's slow to rise, so there is a big inertia in the ice melt. And that's why we, despite already having more than 1 degree warming, only have a relatively modest sea level rise of about 20 centimeters in the last 100 years. But with every little bit of further warming, the rate of sea level rise accelerates. You can see here that for a low emission scenario, that is a Paris scenario, stopping warming below 2 degrees, the sea level rises by about 70 centimeters by 2100, and then it slowly starts to slow down and reaches about 1 meter by 2300. But even though in this blue scenario, the warming has been stopped in mid-century below the 2 degree line, sea level basically continues to rise at a constant rate because of that very inert reaction of the ice sheets to temperature. And if we don't do anything, if we keep increasing our emissions and the temperature keeps going up, then of course the rate of rise of sea level will accelerate. And in a few centuries reach 4 meters, according to the IPCC. And you can imagine what this means to places like this, the Maldives. The Maldives are actually building a new island, which will be 2 meters higher above sea level and relocate much of their people. That, of course, is not possible for many coastal locations. You need very shallow ocean with plenty of sand at the bottom that you can just pile up to build a new island. In most places, it's very difficult to do anything about the rising sea level other than just giving up coastal cities. Another oceanic change is this pattern that you see here that is what a climate model predicts. This one is from Princeton, very high resolution climate model. For a CO2 increase, you see a peculiar cooling south of Greenland of the ocean surface temperatures and a very strong warming of the North American coast there. The data show what's seen on the left here. Of course, we only have patchy data from the ocean observations from ships, etc. But this is a trend for the last 120 years that you see there. But you can see that there is this kind of fingerprint pattern in the Northern Atlantic, which we also see in the model simulation that is happening also in the real world. And in the model, we know exactly why. It's a slowdown of the Gulf Stream system, which causes this pattern. So what we argue is that we are seeing a fingerprint pattern of a slowdown of the Gulf Stream system. That's another prediction of climate models come true. Let me say a few words about tipping points, because they are much debated in the public and few people understand what they exactly mean. This diagram is actually quite in a way, a drastic artistic representation, but in terms of physics, it's very accurate. Imagine this ball rolling in a pot here, and if you push it a little bit to the right, it will roll back to the center, pulled by gravity. So there's a restoring force that brings it back. So this is a kind of stable system, but it does have a tipping point right here. If you push the ball beyond that point, then it won't roll back. It will start rolling by itself in the other direction, in this case here in the fiery abyss. But you don't have to take this so literally, but it illustrates what a tipping point is. It is the point where the further evolution becomes self-amplifying, whereas before that, the evolution of the system was kind of stable. It was always tending to go back to a stable equilibrium. And this is very standard in any kind of nonlinear physics, that this kind of tipping point occurs, and it occurs in the climate system as well. We published a review of this just less than 2 years ago in Nature. an overview over the various tipping elements, as we call them. That's the parts of the climate system that exhibit this kind of tipping point behavior. And you can see there's quite a few of them. The Atlantic Ocean circulation is part of it. The Amazon rainforest has a tipping point where it basically starts to dry up and then probably go up in flames. The term tipping point and tipping behavior is, of course, well known from ecosystems. But as I mentioned, it's also very prevalent in physics. Example, just to give you one specific example, Greenland ice sheet is melting and it has a tipping point because of the ice elevation feedback. This ice sheet is 3,000 meters thick. That's why the surface is in the very cold, higher reaches of the atmosphere, like in the high mountains. And when it melts back, the surface gets lower and lower. And this process then, of course, leads to the surface getting into warmer air and melting even more. So it's a self-amplifying effect of warming and melt back of the ice sheet. And that is there is a tipping point where this becomes just a vicious cycle, and you can't really stop it even if you stop global warming, you won't stop the melt back of the Greenland ice sheet. If the Greenland ice sheet is lost altogether, this will be 7 meters global sea level rise. The tipping point is somewhere between 1 degree global warming, and 3 degrees. We're already at 1.2, so we're in the risk zone where we could pass that tipping point anytime, or maybe we already have passed it. You couldn't even tell for sure because nothing very drastic happens at the point where you pass this tipping point. It doesn't mean the melt back gets suddenly faster or so. It just means from here on, it will just continue until the entire ice sheet is lost, even if you stop further warming. Now, what can we do? How can we get this under control? The goals are good that were agreed in Paris, exactly 50 years, by the way, after that first Revell report from 1965 that predicted all this, the consequences of fossil fuel burning. And the Paris Accord has sharpened the previous agreement of a 2-degree limit to a well below 2 degrees, and hopefully at least stopping warming at 1.5 degree, because it was realized in the light of new science that us scientists basically had underestimated the consequences in earlier years, and we now realize that stopping warming at 2 degrees is not enough to avoid a dangerous climate change, and that's why that goal was sharpened to 1.5 degree aspiration. Can we still hold that line? My answer to that would be yes. There's often the misunderstanding that more warming than 1.5 degrees already baked in by the past emissions, but that's not actually what the science says. It is true that there is thermal inertia because of the ocean heat storage. The system is kind of lagging behind what you've already formed. Yeah, I was just pointing out that the simple formula proposed right after the Paris Agreement is to cut emissions in half every decade. And then we would cut them from 40 gigatons per year in 2020 to 5 gigatons in 2050. And we can hope to ramp up carbon dioxide removal from the atmosphere up to 5 gigatons per year, and that would mean climate neutral. I do think that's very optimistic, though, that we could get so much negative emissions by that time. I think we might have to actually reduce the positive emissions, so I mean the real emissions faster. And I just, at the bottom here, you see a number of just a small sample of the policy measures needed to achieve this transformation of the energy system and climate neutrality. These are just a few examples. I was at a conference on Monday in Germany by the Foundation for Climate Neutrality here, which presented a handbook with 50 measures, policy measures by the German government that would actually bring down our emissions to climate neutrality by 2045. And it's worth taking a look. None of these things is really surprising. For a long time, for many years, all the policy measures that are needed have been debated, and the point now is to implement them. And we have to be really fast because every delay is very costly. We have, had we started right after the Paris Agreement 2015, so in 2016, with lowering the emissions, we could have followed that green track and reach zero just before 2050 and still land at 1.5 degrees. The orange and the red solid lines, they reach the same climate goal because it's the same area under the curve, and but they get steeper and steeper because you start later with emissions reductions. And so this is a key point to understand. The cumulative emissions count. And so with every year that we don't lower the emissions, we are eating up our emissions budget and we have to be at zero earlier. So the key strategy is to lower the emissions as fast as possible now to gain a little bit more flexibility towards the end where the emissions are coming that are very hard to get rid of, like agricultural emissions. And if we just delay another 5 years, the red curve, then basically there's no more chance to reach the 1.5 degree goal. We would overshoot it. And that is what we're up against. We have simply delayed for too long, and now it has to go really, really fast. And that's thanks to all those lobbyists that were spreading misinformation about the science. That makes it all much more expensive now. With that, I'm at the end. Just to sum up, global warming is unequivocal. It's ongoing. There's no doubt about this. It's human cause. There's no scientific doubt about this. And the impacts are not subtle. See all the weather extremes and around the world already. It's not a prediction. We're right in the climate crisis. And to stop the global warming well below 2 degrees is a race against the time now to reach zero emissions. Thanks to all those people that delayed this and doubted the science and all these things. The government commitment to actually reach the Paris goals is far too weak. But there is hope now that we're reaching a tipping point, also partly thanks to Fridays for Future, partly thanks to the increasing extreme weather, fires, all these things that people are really starting to notice we need to act now. And every year counts. And with that, I'm looking forward to the discussion. And if you want to read more, I've co-authored these books. And of course, you're very welcome to look at our Real Climate blog, or follow me on Twitter or other social media. Thanks very much.
Thank you so much, Stefan. We've had some questions from the audience. And the first is, in your view, what is the most effective way to cut emissions?
Can you repeat that? I didn't get it.
In your view, what is the most effective way to cut emissions?
Well, as I mentioned, it's not one way because obviously, we have to get out of fossil fuels, so that's clear, but the policy measures needed for that are manifold, depending on which sector, whether you're talking about the transport sector, the building sector, industry, or the energy sector. In the energy sector, it's clear you have to just replace fossil fuels with renewable energies. We can have the nuclear debate, but personally, I don't think that nuclear power can be ramped up fast enough. I think exponential growth is much easier to achieve with mass-producible renewable energies. Germany last year had more than half of its electricity supplied by renewables, and that was just from near zero in less than 20 years. We ramped that up. One key measure, I think, is carbon pricing. It shouldn't be free to pollute the atmosphere with carbon dioxide because it is a hidden subsidy, because we are not actually, the polluters are not paying for what the damage they are causing, which amounts to a hidden subsidy, which is huge. The International Monetary Fund estimated that as 6% of global GDP go for this hidden subsidy for fossil fuels. That's crazy. We can't subsidize the stuff that we're trying to get out of. basically it's subsidizing our suicide, to put it very bluntly.
Mm-hmm. And speaking of the energy industry, do you think we're on the right track? Or if not, what do you think needs to be done to ensure that we can reduce carbon emissions in the energy industry?
Well, I think in one sense we're on the right track, since we've seen a phenomenal growth of renewable energies. We've seen a phenomenal drop in price in renewable energies, but it does actually require government policies to still accelerate this process, even though it has gone much faster than expected. I've become, over the last 20 years, much more optimistic that we can solve this problem because of this tremendous technological progress. But government policy is still very important, because a lot of big infrastructure like electricity grids are involved, and it just needs a plan. You can't just let this develop entirely just by market forces, although you can, of course, utilize those.
Another question from the audience. If we continue on the track that we're on, how would you foresee summer in Germany to be in 2050?
Well, I think we would get increasing drought problems. We already have them now, and it's easy to imagine how this could get a lot worse. I live in Brandenburg in the east of Germany, where we have hundreds of forest fires every year, and this problem is bound to get more severe. We have seen major forest dieback. I think, of course, we have seen extreme flooding events, the Elbe flooding, the Oder flooding, the Danube flooding. Then we have seen droughts where the Rhine barely carries enough water for shipping or for cooling the power stations that are on the Rhine. We have a lot of problems already now, and this mass mortality with heat waves. There's a picture that I now often show in talks, which shows the mortality in France over the last 50 years, every year. And you see the mortality peak due to the 2003 heat wave is much higher than the COVID-19 mortality peak. The total amount of death is larger with COVID-19 because it lasts longer than that heat wave. The pandemic, of course, is not just for 2 weeks, unfortunately, but the total mortality rate was much higher, and this is a big problem.
And final question, obviously you're a renowned climate communicator. Where do you experience the most resistance from people, and what do you find is the biggest challenge in climate communication?
Well, I think the biggest challenge probably is simply due to well-funded lobby organizations gaslighting all the time. They're putting out these pseudo studies and try to discredit climate scientists. There's hundreds of millions of dollars have been spent in the United States alone on disinformation on climate change. And of course, you have particular media outlets like the Murdoch media, including Fox, or you have Breitbart and things like that, which are simply, from a scientific point of view, systematically spreading disinformation. And I think this is the biggest obstacle to actually solving the climate crisis.
Well, that's definitely a big part of what we're trying to do here, is try and get the right information out there and spread the word. So thank you so much for coming today, Stefan. It was really insightful, and we're really grateful that you could make it.
My pleasure.
Thanks.
Have a good remaining conference.
Thanks very much.